Calc students, to the homework help video. These 4 pages here, all of these numbers. Let's go ahead and get started, okay? I do go pretty fast through these problems. I have already pre-written the steps, so all I'm going to do is just click through the pages, okay? So I like to do that a lot with word problems, so you'll have to pause the video quite a bit, but that's okay. Doesn't hurt anything. I still explain the math as slowly and as well as I usually do, which I hope is usually well, but everything's already written, so you will have to pause the video a lot, okay? Alright, let's go ahead and get started with number 87. Find the number of units sold that yields a maximum revenue for a company that produces health food supplements. Now they give us a model. Revenue R is given by this formula, or this function, when X is the number of units sold. So do you not see what this does for you? I can tell you, you sold 500 units. You put 500 in for X, and out will pop the revenue that you made in dollars, okay? Alright, so they want us to find the maximum revenue. Got it? Now understand, first of all, this is a quadratic equation. See that? X squared. Notice your A term right here is negative. That means the parabola looks like this. So your maximum revenue, your maximum R, is going to be right here at the vertex. So I like to give a picture of this. So I went ahead and drew a picture, okay? This is not my y-axis. This is my r-axis. This is my x-axis, okay? Now, in fact, I kind of contradicted myself. This should say x comma r, not x comma y. So I'm looking, I want to find, actually, let me turn to that page. I did not copy the whole problem, did I? Hold on 1 second here. Okay, I'm back. I did copy the whole problem. It says it right here. Find the number of units sold that will yield a maximum revenue. So we're looking for X. Now we're looking for, let's say it's 800. We're looking for the units that will give us out a maximum revenue. Well, the maximum revenue, like I said, is going to take place at the vertex, the highest point on the graph, okay? So with that in mind, I know if I go over this far, that's my X value, and up this far, that is my R value. Should have an R right there, not a Y. My R value, okay? So we know how to find the vertex, do we not? Negative B over 2A. So there it is. So let's go ahead and write this in standard form. Usually your X squared term comes first, then your X term, then your constant term. In this case, 0. Alright? So here's my A, here's my B, and here's my C. Okay? So for A I put negative. Let's see. For B, I put negative. I put 900. There's a negative sign here, and I put 900 for B. And then for A right here, I put negative 0.1. Here's my A, here's my B. Now if you simplify this, you will get 4,500, okay? So students, we're really done. Your X value is 4,500. So you're over 4,500. That's your X value, okay? They did not ask us to find the actual revenue. Now, if they wanted to know the revenue, then you'd have to take your X value, 4,500, and put that in for X and get out the revenue. They did not ask for that. They simply asked for the number of units sold that would give us the maximum revenue. And this is the highest point on the graph. So we know this is our maximum revenue. And here's the amount of units that we need. 4,500. Okay? Really not that difficult. Number 89. Now this one's a little different. They want to know how many fixtures or how many units should be produced to give us a minimum cost. As a business person, you want to try to maximize your revenue. You want to try to minimize your cost, okay? So the daily production cost, C, in dollars for a manufacturer of lighting fixtures is given by this right here, where X is the number of units produced, okay? So I can tell you we're going to produce 200 units, and where there's an X, you put 200, and you simplify, and it will give you out the cost. You will know how much it costs to make 200 units, okay? So they want to know how many fixtures should be produced each day to keep the cost down to a minimum. Now notice once again we have a quadratic. makes sense because your vertex is now a low point. It's a minimum. In fact, they give us a picture of it right here. Here's the picture. So it's the parabola's right here. Here's your minimum point. So that's really what we're trying to deal with, okay? We have our x value, and I think I keep putting y on the future pages coming up, but it should really be a c. You can put in an x and get out a c value, okay? So we're trying to find the minimum cost, which is this point right here. So x and y, I go over x and I go up y, or c. We'll just call that c, okay? So I'm looking for the vertex once again, guys. The vertex of a parabola. So there's my formula, negative b over 2a. Now remember, this would be your a. This would be your b, negative 10. So where b is, I'll put negative 10. And where a is, I'll put 0.25. Now there's already a negative sign here, so when I put negative 10 in, negative made it a positive 10, and then 2 times 0.25. Now if you simplify this, you will get 20. Now listen to me, students. If the problem would have asked you for the cost, remember it's x, let me get rid of this, it's x comma c. If I would have asked you for the cost, then you take this and you put it in for x right here in this equation and get out the cost. But that's not what the problem asked. They simply said, tell us how many fixtures or how many units should be produced to give each day to yield a minimum cost 20. So the answer is 20. 20 units should be produced, okay, to give you a minimum cost. Alright, moving on to 91. Maximum profit. The profit P in dollars for a plastics molding company is given by this, where X is the number of units sold. What sales level will yield a maximum profit? Okay, same problem again. A lot of redundancy, but good practice, okay? Alright, now, first of all, notice we have our equation here, our function, and it's a quadratic. I want to know what the maximum profit is. Well, here's my x-axis going this way. Here's my p-axis going this way. Here's my maximum profit right there, my vertex. My vertex will help me find the maximum profit. So, there's the graph. Okay, there's the x, y. Now again, I really made a mistake on this. I should have used p's and c's, okay? This should be x comma p. X comma p, okay? You tell me how many x units I have, and I will tell you the profit that we have. Okay? So that means I'm going to find the x going over, and I'm going to find the profit going up. Okay? Alright. So once again, we're dealing with a vertex. So we're going to use our good old formula we've been using, negative b over 2a. So this is my a. Let me go to the next page. This is my a. This is my b. Alright, so this is my a right here. This is my b. So where b is, I put 140. Brought the negative sign over. For a, I put 0.0002. Now when you simplify this fraction, you will get 350,000. Now students, listen. If I asked you to tell me the profit, then you would pick this up and you would put it in for x here, do all the simplifying and get out the profit. But it's not what it asks you. It says what sales level will yield a maximum profit. Well, the answer is 350,000 units. If you make that many units, you will make a maximum profit. By the way, if you start making more than that, notice your profit starts going down. That could be to increase cost. That could be to hiring more people. Whatever the situation might be, you start making less money. So it's not always true. The more you make, the more product you make, the more money you'll make. And that's why these models are really helpful, and that's why companies use these. Alright, number 93. The height, y, and feet of a ball thrown by a child is given by this model here. Okay, so here's the child, and he throws the ball like this. Alright, now, x is the horizontal distance, obviously, from the point at which the ball is thrown. How high is the ball when it leaves the child's hand? Now, be very, very careful here, okay? If you put this as the origin and you set up your graph like this, you've got a problem. The ball's going to go underground. Do you see what I'm saying? The ball's going to have negative. negative distance here. So I'd be really careful on doing that. I would set your graph up like this. I would say where the ground is your x-axis, okay? And then where the person standing is your y-axis, and they release the ball right here, okay? That's what I would do. So it looks like this, okay? Here's your coordinate plane. We'll call this y. We'll call this x. And here's where they release the ball from. So we have to find this distance right here from here up, okay? That's question number one. How high is the ball when it leaves the child's hand? So if you'll think about it, students, we're really just looking for an ordered pair right here. We're looking for an ordered pair that's 0 on the x and something on the y, right? This ordered pair right here is on the y-axis. So how far to the right is it? 0. How far to the left is it? 0. So we know the x value is 0, and then we're looking for the y value. So really we're looking for the y-intercept, to be honest with you. So you're putting 0 in for x. Well, students, that should be really easy to do. Everywhere there's an x, just put a 0 and you'll get out your y. So y-intercept. Here's an x, put a 0. Here's an x, put a 0. 0 squared times 1/12 is 0. 2 times 0 is 0 plus 4. 0 plus 0 plus 4 is 4. So just like that, we found the height of the ball when it left the child's hand. That was pretty simple. Now what is the maximum height of the ball? So now we're dealing with the vertex, correct? Sure it is. We're going to try to find the vertex so that we'll know how high the ball was at its highest point, okay? The vertex. So here we go. I'm going to go over x and up y. How do you find the vertex? Well, you know how to do it. Negative b over 2a. So here we go. Let's use our formula. Here's my a right here, negative 1/12. Here's my b here, positive 2. There's already a negative sign. I put a 2, negative 2. Here's an a. I put negative 1/12. Now if you use a calculator and simplify all this, 2 times negative 1/12 is negative 1/6. So you really have negative 2 over negative 1/6. And if you type that into your calculator, you will get out 12. A negative over a negative is positive, and 2 divided by 1/6 is 12. So there, now we know how far over the ball is. Now you've got to pick up your 12 and put it in for x. Put a 12 here for x, put a 12 here for x, and you'll get out the y value. So now for my x right here, I have a 12, okay? So I'm over 12. Now let's find the height by putting 12 in for x. Well, here it is. Here's all the work, or all the substitution. If you simplify all of this, you will get 16. So now I know that the ball was over 12 feet and it was up 16 feet in the air. That's the highest point of the ball. Now how far from the child does the ball strike the ground? So if you'll think about it, students, now we're trying to find this point right here, are we not? Sure we are. They threw the ball and it hit the ground here. How far over is the ball from the child? So we're trying to find this point right here, okay? X comma 0. Now we know y is 0 because when the ball's on the ground, how high is it? 0. How low is it? 0. It's at 0. So basically to find x, all I have to do is take 0, put it in for y, and I can find x. It's really not that difficult. So here we go. Where the y is, I'm going to go ahead and put a 0, okay? Now for me, I don't like fractions, so I'm going to multiply everything by 12. When you do that, you get this, okay? Now next, it's not factorable. You cannot factor it, so you're going to have to use the quadratic formula. In case you have forgotten what the quadratic formula is, here it is, write this down. Negative b plus minus the square root of b squared minus 4ac all over 2a. Now you're pre-cal students, so I don't reteach this material. You should know by now how to use the quadratic formula. This is your a, negative 1 is your a, positive 24 is your b, positive 48 is your c. Okay, negative 1 is your a. So if you make those substitutions correctly, it'll look like this. Negative 24 for your b, put your b right there, and there's already a negative sign, then b squared minus 4. Now where'd I get 48? AC, a times c, negative 1 times 48, negative 48, all over 2 times a, 2 times negative 1. If you simplify, you will get this. Now you understand distance can distance from the child, okay? 25.86 is your x value, and that is the answer down here, okay? 25.86 feet. Hope that makes sense. Let's continue on. If you have any questions, don't hesitate to back it up and watch it again, okay? Make sure you understand it. Alright, number 95. Number 95. The number of board feet in a 16-foot log is approximated by this model. Now, we really don't need to know what a board foot is, but I'll read it to you anyways, okay? A board foot is a measure of volume equivalent to a board that's 12 inches wide, okay? Excuse me. It is the measure of volume. One board foot is the volume equivalent to a board that's 12 by 12 by 1 inch thick, okay? That's a board foot. And I'm sure it's important when you're working in lumber to know how many board feet you can get out of, or board feet you can get out of a log. So there's a model for that, guys. Here it is. If the log is 16 feet long, and then you know what the diameter, x is the diameter. If you have a 16-foot log, so all you have to do is make sure your logs are cut 16 feet, okay? And you know the diameter, then put the diameter in for x, and you will get out how many board feet you have. So first of all, they tell us to use the graphing utility to graph the function. Now, there's really not a need to do this. My only concern by skipping these, there's one area I'm a little afraid that you guys might mess up on, okay? And that here's this area is your window. So maybe we should quickly type this into your calculator and make sure you guys really understand how to get your windows, okay? So I'm going to go to y equals 0.77x squared minus 1.32x minus 9.31, okay? Now, listen carefully. I noticed I want my x-axis to go from 5 to 40, so right away I'm going to go to my window. So push your window button, go to x, and I'm going to make it go from 4, my x minimum 4, and my x maximum to 45. Actually, I'm going to go from 0 to 45. So I'm going to go 0 for my minimum and 45 for my max. Here's why I'm doing that, guys. I'm trying to get a really big picture of the graph. Now, if you go to your table of values, you want to go to 5 and kind of see 5 gives you out 3.34. Go to your table of values, and you will see 5 gives you out 3.34. Now, continuing on, I'm just scrolling through my table of values. I see when I get to 40, it's going to be really big. I can see right now 40 is going to be up to, my goodness, 1,169. Now, why is that important? Because you've got to fix your Y window. You know that 5, hold on 1 second, students. You know that 5, if I get my pen to work here, gives you out a Y value of 3 point, or a volume of, or a footboard of 3.34. 40 gave you out, what was it? I think it was something like 1,169. So basically 1,170. So now go to your Y window and make your Y minimum 0 and make your Y maximum, I don't know, 1,200, and now hit graph, and you should see a pretty good graph of the function. It'll look like this, like that on your window. Okay, and your window will look something like that, kind of like that, not perfectly. Actually, this will be down more, like that right there. Okay, but nonetheless, my only concern is you guys don't know how to use your windows well, so make sure you can do that. Okay, letter B. Estimate the number of board feet in a 16-foot log with a diameter of 16. So remember, if my diameter is 16, then everywhere there's an X, I'm going to simply put what? 16. Now, this formula only works when the log is how many feet long? 16. And notice it says you have a 16-foot log, okay? So everywhere there's an X, I'm going to put a 16. Not because of this 16, because the diameter is 16 inches. So there we go. Everywhere there's an X, I put 16. Now I simplified that, and I came up with this. So there's 166.69 board feet in one log that has 16 feet long, that has a diameter of 16 inches. Now, next, they want us to go backwards. They're going to give us the board feet, and they want us to estimate the diameter of a 16-foot log. So now we're going to have to pick up 500 and put it in for V, the board feet. Okay, so where V is, I'm going to put 500, and now I've got to solve this. So guys, you know what to do. Bring your 500 over. It's a quadratic equation, so we want to get one side equal to 0. Move the 500 over and make it negative. When you do that, you'll have this. Now, here's where it gets, excuse me for yawning, here's where it gets a little difficult, okay? You can use the quadratic formula, which is a great thing to do, okay? And it will give you the right answer. Or you can use a graphing calculator, type this into your grapher, and look for your x-intercept. And that's fine too, okay? Either way works. If you use the quadratic formula, you'll have this right here. And then we'll simplify it down to this right here. Guys, I'm not being lazy. You're gonna have to learn to do that on your own. You're either gonna have to type this into your graphing calculator and then look for the x-intercept. Make sure and fix your window so that it fits your data, or you can use the quadratic formula. Okay, but either way, and if you did use your quadratic, if you did use your grapher, you would see the graph will cross the x-axis at 26.6, okay? So that's the diameter you would need from a 16-foot log to get 500 board feet, okay? Alright, moving on to number 88. Alright, now this is a pretty tough problem, so if you'll pay attention I can help you, but really, really pay attention, okay? An open box with locking tabs is to be made from a square piece of metal 24 inches on a side. This is done by cutting metal squares from the corners and folding along the dashed lines as shown in the figure. So we're going to take away 2 x's here and fold it up like this, and then also fold it over so it comes over, okay, and probably folds down in there into a little tab. Same thing with this side, okay? So both sides of metal are originally 24 by 24. Both sides are 24 inches, but then we're going to cut part of it away, okay? So verify that the volume of the box is given by the function, okay? Now watch carefully, please, what I do. After you've made these folds, we have taken part of the x's away. Watch carefully. See this side right here? You have taken away 2 columns x length, okay? So now it's smaller, and you also took 2 x's away over here on this side. So now this entire width right here only goes from here to here. So that's 24 minus 4x. You took 4 x's away. Now, this length here had 1 row of x's cut away here, 1 row, and had 1 row here of x's cut away. So now the length of this side right here only runs from here down to here. So we lost an x here, and we lost an x here, so it's 24 minus 2x. Now the height is x. Why do we need the height? Because we're dealing with volume. Volume is what? Well, volume is length times width times height, okay? Length times width times height. So here we go. For the length, I'm going to put 24 minus 2x. For the width, I'm going to put 24 minus 4x. And for the height, I'm going to put x. Now we're going to simplify this and see if it matches this right here, because letter A says verify that the volume is this right here. So here we go. First of all, in the first parentheses, I can pull out a 2. Okay? And in the second parentheses, I can pull out a 4. So pull a 2 out of this parentheses, and you're left with 12 minus x. Out of this parentheses, pull out a 4, and you're left with 6 minus x. Now remember, all of these groups are being multiplied. You have this group here, times this group here, times this group here, times this, times this. Everything's being multiplied. Remember, when everything's being multiplied, you can put them whatever order you want. 2 times 3 times 4 times 5 is the same thing as 5 times 3 times 4 times 2. You can put them in any order when you're multiplying. x. Then bring this down, and booyah, look at that. This matches this exactly. So there we go. We verified this is the volume. Now we're going to determine the domain of the function v. This is really, really tricky. So please listen to me carefully, okay? When it comes to finding the domain, we know for sure right off the bat your domain is your x value. Well, x, because we're dealing with lengths and all of that, we know x has to definitely be greater than 0. You can't have a negative length. That's called a common sense constraint, okay? But now be careful with the other aspect of the domain. Excuse me. For example, let me show you something here. 6 minus x, watch this. If I set that equal to 0 and solve, bring the x over and bring the 6 over and make it negative. Now divide by -1, watch what happens. I get 6, so that means 6 makes this parentheses a 0, okay? But what if I put a 7 in there? I get out a negative number, and that's going to make this whole thing become negative. I can't have that. How does it make the whole thing become negative? Watch, guys. If I put a 7 here, 6 minus 7 is -1. 8 times 7 is 56. Put a 7 here, 7 minus 12 minus 7 is 5. A positive times a negative times a positive is a negative number. You cannot you cannot use a number for x here that's greater than 6. You can't. It has to be less than 6. If you put 7 or 8 or 9 or 10 in, you'll get out a negative number. And you can't put 6 in because that gives you out 0. Okay? So what I want to show you is x has to be greater than 0, but x has to be less than 6. Now the same thing happens here, guys. You cannot put a 13 in, or a 14, or a 15. You can't put anything in bigger than 12, or you'll get out a negative number. Do you not see that? We can't. Now you might not have thought of this on your own, but hopefully you're seeing it now that I'm explaining it to you. You could not put 13 in this parentheses, or 14 or 15. Because it would give you out a negative number, okay? And we can't have that. Now, so with that in mind, we're going to have x has to be less than 12, okay? So, with that in mind, what is the domain going to be? Well, look. X, let's go back a couple pages here. We have to have a domain where all three of these agree, okay? So we know x is greater than 0, fine, here's 0. Here's 0. X has to be greater than 0, fine. However, this constraint here says less than 12, fine, less than 12, but this constraint here says less than 6. So we've got to go with where they all agree, and all three of them agree right here, in that area right there, greater than 0. I mean, less than 6 is also less than 12, but less than 12 is not necessarily less than 6. So the area they all agree is right in here. So the domain would be x is greater than 0 and less than 6, okay? Now sketch the graph of the function, estimate the value of x for which v of x is maximum. Again, students, I'm not really getting into the graphing part on this. We've done a lot of those. I will say this, on a test or quiz, if I asked you to graph this, you would type into your grapher, that'd be fine to do. And make sure you get the appropriate window in. Okay, your window is very important, or the graph will not look right on your screen. And then you can estimate the height, the value of x for which the volume is the maximum. Okay? Alright, moving on to number 95. Now be very careful here. A rectangular package to be sent by a delivery service can have a maximum combined length. Here's my length. And girth. Girth is the perimeter of the cross section. Okay? So it can have a maximum combined length in this perimeter of 120 inches, okay? First of all, they want us to show that the volume of the package is given by this right here, okay? They want to show that. They want us to show that this is truly a model or a function So we can say length times width times the height, okay? Now all of these are x's back here, so I know for w I'm going to put x, and for my height I'm going to put x, but my length is what? Y. So I've got to put a y in there. That's not going to work, guys. I'm not doing 3D graphing or 3-variable graphing. I've got a v, a y, and an x. So here's what I'm going to have to do. I'm going to have to come up with a formula in which I can get rid of this y, and here it is. Remember, they really didn't word this very well, but we are assuming we have the maximum girth. They should have said that. So if I take my perimeter x, by the way, if this is x and this is x, which it is, then I can call this x and this x and this and this. So if I take my perimeter x plus x plus x plus x, I get 4x, then plus my length, which is y. So 4x plus y equals 120. Now, do you not see what I can do? I can get y by itself like this. And now y equals this. So I can pick that up and put it in for what? In for y. Okay? So bring the 4x over and make it a negative 4x. And now y is by itself. So now where the y is, I'm going to put 120 minus 4x. Now let's simplify very quickly. Okay? First of all, in this parentheses here, you can factor out a 4. So if you factor out a 4, you're left with 30 minus x. So then we have 4 times x times x. So 4 times x gives you 4x squared, and then bring down your 30 minus x. So yes, we just proved that the volume is this right here, okay? So that model there is a good model for the volume. Now, use the graphing utility to graph the function and maximize the dimensions of the package that yield a maximum volume. I think I'm going to go ahead and do this one, so please follow along and take some really good steps or notes on this, okay? First of all, I'm going to type this into my graph or so. Go to my y equals, clear out my screen, and type in 4x squared, and then parentheses 30 minus x, close my parentheses. Now, I'm going to, after you've done that, students, listen carefully, go to your table of values, okay, and just kind of look at what kind of y values you're getting out for some of your x values, okay, because they're looking like really big values to me. Okay, there's no way x can be 0. That would be a 0 length, you understand? Okay, so, I know I want my x window to have a minimum of 0. Now, let's see here, guys. How are we going to figure out what my x max should be? Let's think about this for a second. Well, students, here's how I knew what I wanted my x maximum to be. I went to my table of values, and I realized I wanted my x's to start at 0. So go to your table of values and look at 0. Now just hold down the arrow button. Just kind of scroll through your values. Just hold it down and watch. Just hold it, scroll, and you'll see that the values are getting bigger and bigger. And hold it, stop. Did you notice at 20 it was 16,000? 20 gives you 16,000 now, so it's going down lower again. See that? Okay. And at 30 it goes back to 0. So I said to myself, okay, I'm going to make my maximum go from 0 to 30, so I'll make it 35. Now, along that path, when I was holding my scroll button down and scrolling from 0 to 35, the biggest y value I ever got, the biggest y value was 16,000, I think. So I'm going to set my maximum at 17,000. And I'm going to go ahead and put my minimum at 0. Alright, so let me get my window open. So my x minimum is 0, my x max is 35, my y minimum is 0, my y max is 17,000. Now hit graph, and you should get a pretty good graph. There it is. Now that's not the entire graph, but that's good enough for what you want. And it should look something like this. Here's your computer screen if you've done it correctly. It should have, come up like this. Come up, peak, and then come down pretty quickly like that, okay? Now, you're looking for this maximum point because it says, use a graphing utility to graph the function and approximate the dimension of the package that yields a maximum volume. Maximum volume. So I want the highest point. So I've got my x, which is my length and my width and my height. I've got my x, and then I've got my v, my volume. So let's find the dimension of the package that gives the maximum volume. So let's see. Second calculations. Go down to maximum. Hit enter. Okay, left bound. Hit enter. Go to the right of the maximum. Hit enter. Then hit enter on guess, and it's giving out something like 20 for x and 16,000 for y, which I think we already knew that. So the maximum volume, the dimensions would be 20 by 20 by 20 by 20, okay? And then we already know, if you'll think back, we had a formula that said 4x plus y would give us our total girth. And so we know our y would have to be 4x plus y equals 120. So we have 20, 40, 60, 80. Then this right here would have to be 40, because you add up your perimeter. 20 plus 20 plus 20 plus 20 is 80, plus 40 is 120. So there we go. So what are the dimensions of the package that give us a maximum volume of 16,000? Well, x is 20. So if x is 20, then it's a 20 by 20 by 40 dimensions. Now, next, part C says, find the values of x such that v is 13,500. So now we have to put 13,500 in for v right here. Okay, so when we do that, we get this right here. So guys, we got some work to do. First of all, you simplify the right side. Take this and multiply it through. Then you notice you have a cubic function, third degree. So you want to get one side equal to 0. So you're going to bring this over. Bring it over and you're left with this. And I've written it in standard form. Now next, divide everything by -4. I don't want my first term to be negative. And 4 goes into all these numbers. So divide by 4, -4, and you're left with this. Now students, look, on a test or a quiz, I'm not going to give you a problem like this and tell you to list out all the possible rational zeros by using the factors of 3,375. That's crazy. So you're welcome to use a grapher or whatever you want to help you find the x-intercepts, okay? And if you do that, you will see 15 is one of your zeros. So 15 solves this equation. If you put 15 here, which I'm not going to do, and did synthetic division, put a 1 here, and a -30 here, and a 0 here, and 3375 here, in the end you will get out a 0. So one of your zeros is 15, so x minus 15 is a factor, and all the numbers here you're left over with would be this right here. Okay? Now, moving on. Next, if you take this right here, it's not factorable, and you use the quadratic formula, you'll come up with this right here. Now it says, which of these values is a physical impossibility in the construction of the package? Well, the negative is, guys, there's no way you can have out a negative x. It's impossible. So you don't want the negative sign here, because 15 minus 15 square root of 5 divided by 2 gives you out a negative, okay? So you're going to end up with 15 is one of your answers. And then 15 plus 15 square root of 5. Let me type that in real quick, just to get an idea of what that decimal would be. 15 plus 15 square root of 5 would give you 48.54. 48.54. Okay? So there's two different options for your x, okay? And the one we would not want is the negative sign here, okay? So there we go. Moving on. Number 97. Alright, the order and transportation cost C in thousands of dollars for the components used in the manufacturing of a product is given by this, where C is the size, where X is the order size in hundreds. Now, in section 5.1, you will learn in the future that the cost is a minimum when we have this right here. Okay, so since they're telling us that now, use a calculator to approximate the optimal order size to the nearest 100 units. This is really a confusing problem, not by the math part. The math part's pretty easy by how they word the problem, okay? Look, they just want you to simply take this function they give to you, this function right here, and simply solve it for 0. So you're finding the zeros, and those numbers will be the approximate optimal order size to the nearest 100 units. Now, we're not going to focus on where this function came from right here, because they told us we'll learn about it later in section 5.1, okay? But for now, we're going to take this equation here, and we're going to find the zeros, okay? So, the only zero is approximately 40. Now again, here's how I would do this on a test or a quiz. There's no way I want you to list out all the possible rational zeros and test them all when you've got a lead coefficient of 3 and a constant term of 36,000. However, if you'll type this into your grapher and then go to your table of values and figure out your what? Your window is so important. And get a really good graph on your screen. You can then see where the graph crosses the x-axis at. And remember, there is a function under calculations called 0. After you've graphed your line, if you'll go to second trace or calculations, option number 2 is 0. You hit that, and of course the grapher will help you find that 0 that you're looking for. So that's what I would recommend that you do on this type of problem. You cannot use the quadratic formula because you don't have a quadratic. You've got a third degree. You have a cubic function. Okay? So the only 0 that satisfies this equation is approximately 40. Okay? So that would be the optimal order size to the nearest 100 units, by the way. So it'd really be add 2 zeros to that. 40 hundreds would be 4,000. Alright? Okay, moving on to number 99. A company that manufactures bicycles estimates that the profit P in dollars for selling particular models given by this, where X is the advertising expense in tens of thousands of dollars. Using this model, find the smaller of the two advertising amounts that yield a profit of 800,000. So this model here does two things. You can either put in the advertising expense X and you will get out the profit you're going to make, or you can tell me the profit you want to make and I will tell you what your advertising expense needs to be. And that's what they're doing. They're giving you the profit. So where the P is right here, we're going to put 800,000, okay? And that's what we did. Now, if you do this carefully, and you think about it, you're going to see right away you have a cubic function. So you know you want to get one side equal to 0. So we're going to take the 800,000 and bring it over here. Alright, so when you do that, you end up with this right here. Now, 45 goes into all these numbers, plus the negative 45. So I'm going to divide every number by negative 45 to make the problem smaller. And that's not true, sorry. 5 goes into all of those numbers evenly. Alright, so we've reduced it as low as we can go. We divided everything by a negative 5. Now again, students, look, all I can tell you is this. There's no way on the test or a quiz I'm going to give these problems to you and tell you to list out the possible rational zeros, the factors for 215,000. So using a graphing calculator, and I'm going to do that real quick because I'm really worried that you guys do not know how to use your windows properly, okay? So with that in mind, let's go to, see, y equals, and type my new equation in, 9x 9x cubed minus 500 x squared plus 215,000. Alright, now I'm going to go to my table of values first of all. I'm going to start at 0 because I know you cannot have, for your x value, you can't have 0. You can't have less than 0 to spend in advertising. It's not going to be negative. So I know my x minimum is going to start at 0. So So for my x here, I want a minimum of 0. Now my maximum, I'm going to kind of look this over here and think this through. I'm going to kind of scroll down, just kind of look at the numbers on the right side, get an idea of what they're doing. Smart to do. I notice they're getting lower and lower. And actually when I get to 31, at 32 they jump down to a negative number. So I'm going to run my x values from 0 to about 35, okay? So window 0 to 35. Now my y values, when I'm at 0 on my table of values, when I'm at 0 on my table of values, I get out 215,000. That might be my smallest one yet, we'll see. Now that's my largest, it looks like. And then it gets smaller and smaller, down to about 0. So this will be my largest y value, and my y value is going to run it down to 0. So for my window for y, I'm going to put a 0 for the y, and then 200 and, we'll say 20,000. 220,000 for my y maximum. Hit graph. And I'm getting a pretty good graph. Should look like this. Here's your computer screen. And it's starting right here. And it's coming down. Little curve. Kind of going like this. Okay. So there we go. So it's looking like I'm going to have an x-intercept right here. Okay. So I guess I better make my y values. I'm going to go to my window and make my y value the minimum like a -5. So the graph will go below the x-axis just a little bit. So now the graph's going to hit, and then maybe go just a little lower, okay? So I'm going to find my 0. So second calculations, 0, left bound, hit enter, then make sure you move past the enter the y-intercept, the x-intercept. Hit enter, then enter again, and I'm getting out approximately 31.53. Okay, 31.53 for my x value. All right, now let's see if that's correct. There it is, 31.5. So also -18 was one of my values. That's not going to help. Here's another one if I would have kept going, 42. But the smallest one is 31.5. That was the smallest 0 that I had on my x-axis, okay? Alright, hope that makes sense. Moving on. Oh, and by the way, it was 31.5 was your x value, but notice x is in $10,000s. Well, 10,000 is how many zeros? 4. So move the decimal 4 places. 1, 2, 3, 4. And that's why you get 315,000, okay? 31.5 is the same thing as 315,000 because it says right here, x is in terms of $10,000s. Alright, number 73. The cost C in millions of dollars of removing pollutants, percentage P of the pollutants discharged into a river is given by this function here. Find the cost of removing 10% of the pollutants. Okay, so I can put in a percentage right here, 10, and get out the cost. So I'm going to do that. So here's letter A, where the P is here and here. I put a 10 in and a 10 in. If you simplify that, you will get 28.33. Now it says it's in millions of dollars, so it's 28.33 million, okay? Now that's really easy, folks. Look, students, if I'm trying to eliminate 10% of the pollutions, put 10% in for P here and P here. So letter B, I'm not going to work out B and C for you. It's obvious what to do for B. You put 40 in for P and P, and you'll get out this right. You'll get out this right here, 170 million. For C, we want to remove 75% of pollutants, so you put 75% in for P, and you'll get out this right here, $765 million is the cost that it will take. Now, according to this model right here, would it be possible to remove 100% of the pollutants? Well, no, guys. If you put 100 in for P, it gives you undefined. Think about it. Put 100 right 0. And you can't have 0 in the denominator, okay? So no, putting in 100 for P gives you undefined. It doesn't work. So no, it's not possible based on this model to remove 100% of the pollutants. Alright, number 75. The Game Commission introduces 100 deer into the newly acquired state game lands. The population N of the herd is given by this, where T is time in years. So I want to know what the population of deer is going to be in 5 years, then 10 years, then 15. So I can put 5 in for T and get out the size of the herd. So everywhere there's a T, I'm going to put a 5, okay? So I do that, and it looks like this. Then I simplify. And 5 plus 3 times 5 is 20. 1 plus 0.04 times 5 is 1.2. 20 times 20 is 400. And 400 divided by 1.2 is 333 and a third. Now I'm not going to do that over and over for 10 and 25. I'll just tell you the answers, okay? When you put in 10, you get out 500. When you put in 25 for T, you'll get out 800. So that's the size of the herd after 5 years, 10 years, and 25 years. What is the limiting size of the herd as time increases? What is the limiting size of the herd? Now listen, the horizontal asymptote limits the herds. Let me show you what I mean by that. Okay, first of all, your function is N and T. Got it? N, T. See it? N by itself, T. So, if I were to draw the coordinate plane, I would have my N right here and my T right here. Okay? So, look, listen students, vertical asymptotes are not going to limit the herd. I mean, I don't care how many vertical asymptotes you have, N can still be going up and down where you want it. But if I have a horizontal asymptote, that cuts off the herd. Okay? So when the question says, what is the limiting size of the herd as time increases? Well, the horizontal asymptote is what's going to limit the herd. A line going across horizontally like this is going to limit your n-axis. Like the graph might come down and get closer and closer, but that's it. So what is the limiting? Let me read the question exactly how they say it, okay? What is the limiting size of the herd as time increases? Well, let me show you first of all how I found the horizontal asymptote, okay? Please take some really good notes. Watch this. First of all, I simplified the top. Take your 20 and multiply it through. 20 times 5 is 100. 20 times 3 is 60t. Okay, next in the bottom I have 1 plus 0.04t. Now, what is my degree up top? 1. What is my degree in the bottom? 1. We learned that when the degree up top is the same as the degree in the bottom, you have a lead coefficient of, you have a horizontal asymptote of lead coefficient over lead coefficient. So my horizontal asymptote is 60 over 0.04. And with your calculator, if you type in 60 divided by 0.04, you will get 1500, 1500. And so that's what limits the herd, okay? 1500. Alright, moving on to page 77. This is an amazingly difficult problem, maybe the hardest one that we're going to do. So I hope you'll take some really good notes and don't get discouraged if you're lost a little bit. Just do the best you can to take notes and follow my reasoning, okay? A rectangular page is designed to contain 64 square inches of print. Okay, square inches of print. The margins at the top and bottom are 1 inch. The margins on the left and right sides are 100 or 1 and 1/2 inches. Excuse me for yawning. Sorry. What should the dimensions of the page be so that the least amount of paper is used? Now, first of all, I think it'd be wise to get a picture of this. So if you want to copy this down, feel free to. The margins along the side are 1.5. Okay, so notice we're taking 1.5 inches away from the width going across. Now the width is only from here to here. Okay. Also notice we've taken something away from the length too. Okay, we've taken an inch away here from the top and an inch away here in the bottom. So the length is only going to run from here down to here. Okay. Alright, so there's a picture of what they're doing, okay? now. What should the dimensions of the page be so that the least amount of paper is used? Alright, what should the dimensions of the page be so that the least amount of paper is used? Okay, so our students had to pause the video there and get a drink real quick, and now let's continue on now. Okay, watch this carefully. This is a really tough problem. First of all, I want to point out to you that your length, whatever it is, the entire length of the sheet of paper is L minus 2 because we're losing an inch here, losing an inch here. The width of the entire paper was W, but now this part from here to here is going to be W minus 3 because we lose 1.5 inches here and 1.5 inches here. The distance from here to here is going to be L minus 2, okay? Now, if we multiply those two together, do we not have the area? Sure we do. Think about that. I mean, obviously, anytime you take the length, which is the distance from here to here, and the width, which is the distance from here to here, that's the area. Well, Mr. Earhart, why are you using just that little bit of space? Because notice it says this, 64 square inches of print. You can't count the margins, guys, when we're talking about the part of the paper it's printed on. So really the part of the paper we're dealing with goes from here to here to here to here. That's where you can print stuff right there. So the area of that is 64, because it says right here 64 square inches. So if I take L minus 2 times W minus 3, I'll get 64. Now just watch what I'm doing here, see if you can follow along, okay? If you simplify, you'll get this. L times W, L times negative 3 gives you this and this. Negative 2 times W, negative 2 times negative 3 gives you this and this. Now I want to solve for L, and you'll see why in a second. If you'll trust me and take notes on this and just watch, you will see why we're going to do that, okay? We're going to solve for L. So, we get all of our L terms on one side. This term has an L, and this term has an L. Get them both on one side. Everything else, bring to the other side, okay? So bring your negative 2W over, make it positive. Bring your 6 over, make it negative. That's 58, okay? Now for solving for L, next I'm going to factor out an L. So pull an L out of this, and you're left with W minus 3. The reason we did that is we can now divide both sides by W minus 3 like that. And when you do that, you're left with this right here. L equals this. Okay, Mr. Earhart, great. We kind of get it, but why'd you do that? Well, let me show you why I did that, okay? Watch carefully. I'm going to go back a page. I'm taking this right here, and I'm going to write it up top. We're going to need that later, okay? So there it is. Now, I want to remind you, area equals length times width, okay? So with that in mind, for the length, I'm now going to substitute this right here, because that's what L equals. Do you see what I'm doing, guys? I'm getting an area in terms of W. I don't have two unknowns anymore. Now I can say the area is length times width. And so where the L is, I can actually substitute this because this equals L. So for the L right here, it's gone. I'm putting this. And now when I put this over 1 and multiply it through the parentheses, I get this right here. So now I have a model for the area of my function, of my situation over here. And that's really, really helpful, guys. I have an area based on the width. I only need one unknown, and that's the width. Okay? So, with that in mind, what should the dimensions of the page be so that the least amount of paper is used? Well, here's what I did. I took this and I put it into my grapher, okay? So go ahead if you want to follow along and do that. I put this in my grapher, okay? And I got this graph right here, okay? The graph's coming down like this and coming over. And then here is going like this. Okay? Like that. Now, I realized right away that I definitely want to look to the right of the W. So I've got a vertical asymptote of 3. I know there's no way that my width can be less than 3 because, my goodness, students, look, I've got a margin here of 1.5, a margin here of 1.5. That's 3 inches alone. I can't have less than 3. So I know I'm looking over here to the right of 3. Okay, and it says what should the dimensions of the page be, so that the least amount of paper is used. The least amount of paper. Well, here it is. There's my minimum right there. So using my graphing calculator, I hit second calculate, then down to minimum. Then it said left bound, so I make sure my little cursor was over here. Then I hit enter. Then it said right bound. I move my cursor over here. I hit enter. Then it said guess. And I hit enter, and I got a 5.8. So now I know what the width is. Okay, this should be an A right here, not a Y. So when my width is 5.8, then I know that I have the dimensions of the width, so that the least amount of paper is being used. So let's go back now. So my W is 5.8 now. Let's go back to when we had this formula right here. Remember this right here? This was an equation that we had earlier during this problem. You should have this somewhere in your notes, and it tells you what the length is. So if W is 5.8, pick that up, and everywhere there's a W, but 5.8. And if you do that correctly and simplify, you will get out 24.9 for the length. So there we go. So what are the dimensions of the page? 5.8 by 24.9. Okay, alright. Moving on to number 79, and we're finally finished. The concentration of a chemical in the bloodstream T hours after injection into muscle is given by that function right there. Now, first of all, determine the horizontal asymptote of the function and interpret its meaning in the context of the problem. Sure, no problem. This is a rational function. The degree is 2 in the top. The degree is 3 in the bottom. Anytime the top is less than the bottom, we have a horizontal asymptote at, remember, 0. So that's easy. We found the horizontal asymptote. Now interpret it in context of the problem. Well, sure, it's so obvious, guys. I mean, no offense, but it's so obvious. Look, you have a horizontal asymptote of 0 because this is your C-axis here. This is your T-axis here, okay? As the constant, look, when you get the shot or the injection into muscle tissue, that's when the chemical's at its highest. It's going to go down. It's going to get closer and closer to 0. Alright, never quite reaching 0. Now you could argue eventually it would be 0 in your bloodstream. Probably so, but I think you get the point they're trying to make. The graph's going to get closer and closer to 0 because the chemicals are slowly leaving your body, but never totally leaving your body. Now, so that's the interpretation of the horizontal asymptote, and that's what the horizontal asymptote would be, is 0. Now, use the graphing utility to graph the function and approximate the time when the bloodstream concentration is the greatest. Now, guys, hold it. Look, we know when the bloodstream concentration is the greatest is going to be the moment you get the injection. I would have to think, okay? But nonetheless, maybe I could be wrong on that a little bit because it does take time for it to get through the muscles into your bloodstream. So let's go ahead and type this in, and let's graph this and see what happens, okay? So in my grapher, I'm going to go ahead. This is a real tough problem because something's going to happen here during the graph, so please watch carefully. Please watch carefully. Okay, put 3x squared plus x. Be sure and put parentheses around that whole thing, and then divide it by, and then parentheses, x cubed plus 50. Now, before you hit graph, let's go to our table and take a look, okay? We know our x value is going to start at 0, t value, whatever. It's going to start at 0. So I know my x minimum, x min, is going to be at 0. Now, as I look at this, guys, I'm scrolling down. I mean, this is really weird because 0 gives me out 0, okay? But then it only goes up 0.0 as I scroll down in my table of values on my calculator from 0 to 1 to 2 to 3 to 4. Look how slow the y's are increasing. 0.24, 0.3, 0.4, 0.5. start going back down, point 0.2, point 0.2, point 0.1, point 0.11. So I'm going to go with 0 for my minimum. I'm going to go with probably 30 for my maximum. But for my y's, my y minimum is going to be 0. My y max is going to be like, my goodness. The highest I saw a number was 0.4. So I'm going to make my y maximum 0.5. Let me go to my window real quick. Let's see. So my y minimum will be 0, and my y maximum is going to be 0.5. Okay, let's hit graph. Okay, so I was wrong. Okay, the greatest concentration is not going to be at 0. The graph looks like this on your graph, or it should. It shoots up, tops out there, and then comes down and makes its way like this. Well, not like that. Makes its way down, getting closer and closer to the horizontal asymptote, okay? So the highest point is going to be here. So with your grapher, hit second calculation, second trace, and then hit maximum point. So go down to option 4, maximum, and then make sure your cursor's to the left of that maximum point. Now mine's way over to the right, so I've got to hold down my button for quite a while to make sure I get to the left. Okay, so it's left bound, hit enter. Now I'm going to move that cursor to the right of that maximum place. Hit enter on that, then hit enter again, and you're going to get out. The x value is 4.5, and the y value is 0.4623. Alright, so it looks like to me I was wrong, okay? The greatest concentration in your bloodstream is going to be 4.5 hours after you get the injection, because that's the maximum point right there on the graph. Okay. All right, guys, that's it. These have been some really tough problems. I know that. I hope these have made sense to you. If you have any questions, don't hesitate to